Good evening everyone, good evening. I welcome you all again back to the NEET Elite. Hoping that you guys are doing great, having the good time. Well people, you can let me know in the chat box if I'm audible and visible to everyone. You can let me know in the chat box with some thumbs ups. Good evening Saurav, hi Ashwarya, hello John, Peter, hello Afreen, good evening. Hi Priya, hi Lekashri. Hello Gayatri, hi Arzu, good evening, good evening. Welcome back guys, welcome back. Afreen, I'm doing great. Well, I'm getting green signal from Priya, that's great, perfect. Alright, good evening Anush, hi Jyoti, hello Madhumita, hello Ashwa, good evening. Hi Karthik, welcome back. Well, Yashwant has come up with a quote after so long. If you're working on something that you really care about, you don't have to be pushed. The vision pulls you. Oh, good evening. That's great, Yashwant. That's great. You have come up with a quote after so long, yeah? Perfect. Just give me a second, guys. We'll be starting. All right. All right, guys, perfect. So as you all must be knowing, today it's going to be our lecture number 4 from the chapter Chemical Bonding, right? In the last session, if you remember, we talked about something called as hybridization, by means of which we got to know how to calculate, how to know the geometry of the molecules, right? By a method called as steric number method. I hope you remember that. Yes. And in the today's session, what we'll be doing right here is, we'll be doing something called as valence shell electron pair repulsion theory, okay? Saurav, it's Wassim, but W-A, okay? Alright, so people will be, in the today's session, we'll be doing something called as valence shell electron pair repulsion theory, right? By means of which, you'll be getting to know how do we predict the actual shapes of the molecules, right? Geometry is different, shapes are different, right? Geometry is something which you expect a molecule to have, okay? Shape is the actual structure of the molecule, yeah? Perfect. So by using the valence shell electron pair repulsion theory, which I'll be telling you in the today's session, you'll get to know what are the actual shapes of the molecules. Perfect. All right, guys. So for the ones who do not know me, let me introduce myself. My name is Wassim and I'm your chemistry master teacher right here on this channel, right? Perfect, guys. For the ones who have not liked the video yet, please do like the video, share and subscribe the channel at the same time so that everyone gets benefited out of these sessions, right? Yes, so do subscribe the channel so that you get the notification of every session of mine whenever I'll be coming live on this channel, on V Elite, yeah? Yes, Kubab, yes. All right, people. So let me know in the chat box if you guys are super duper excited about something called as VSEPR, valence shell electron pair repulsion theory. Let me know in the chat box. Hi Anamika, welcome. Welcome to the session. Let me know in the chat box if you guys are super duper excited for the session. Karthik Sahil sir will be joining soon. Yes, he'll be joining soon. Most probably Monday, Tuesday he'll be joining, yeah? Just give me some green signal from the chat box so that I can move on and get started, right? Hello Anil, good evening. Hi Kurat, hello John Peter. Josh is high as always, yeah? That's wonderful. All right guys, so without wasting a lot of your time, let's get started with something called as valence shell electron pair repulsion theory, okay? Before talking about this valence shell electron pair repulsion theory, let me just give you the quick recap of what all things we discussed in the last session, right? Well people, before talking about this valence shell electron pair repulsion theory, let me just give you the clear-cut idea of what all things we discussed in the last session so that this session you'll feel easy to understand, yeah? See guys, have a look. First of all, in the last session, we talked about something called as hybridization. I hope you remember that. Yes. We talked about something called as hybridization. Yes. And hybridization, it gives us the idea about the geometry of the molecule, right? It gives us the idea about the geometry of the molecule, right? Now people, I gave you one simpler method by means of which you can calculate the hybridization, if you remember. That's something which we call a steric number method. And steric number is always equal to sigma bonds plus lone pairs, yes? And I told you, if the value of steric number for a molecule comes out to be 2, the hybridization of the molecule is said to be Sp. And if the hybridization of the molecule is Sp, its geometry is considered as the linear, okay? The molecule is said to have the linear geometry, right? Similarly, if the steric number of the molecule comes out to be 3, the molecule is said to have the hybridization of sp2, and if the hybridization is sp2, the geometry which the molecule follows, the geometry which the molecule shows at that time, that's what we call as trigonal planar, right? I hope you remember this. Trigonal planar. This is something which we have discussed in the last session, yeah? And if the steric number comes out to be 4, we say hybridization is sp3. Similarly, if the steric number comes out to be 5, we say the hybridization is sp3d, and if the steric number comes out to be 6, we say the hybridization is sp3d2, and at the end, if the steric number comes out to be 7, we say the hybridization is sp3d3, right? And later on, I told you the molecule which has got sp3 hybridization, its geometry is expected to be tetrahedral, right? It is said to have the tetrahedral geometry. Similarly, steric number 5, sp3d, it's said to have trigonal bipyramidal geometry. Trigonal bipyramidal geometry, yes. And sp3d2, it means the molecule has got the octahedral geometry. Yes, sp3d means pentagonal bipyramidal geometry. This is something which I told you in the last session, if you remember, yeah? Perfect. Rajendra, this is the English channel, bro. This is the English channel, okay? Alright guys, have a look now, understand. One more thing I told you, which d orbital is involved in sp3d hybridization? If you remember, it was dz square, yes. Which d in sp3d2 square and dz square, yes. And in case of sp3d3, which all hybrid orbitals were involved in the hybridization? It used to be dxy, dyz and dzx. This is something which we talked in the last session, right? These were the geometries of the molecules, correct? Now people, how will we get to know the actual shape of the molecule? These are something which I call as geometries of the molecule, right? So the idea of the geometry of the molecule I'll be always getting from the concept of hybridization, right? But what about the actual shape? What about the actual shape of the molecule? That I'll be getting to know by one new theory, which is what I call as valence shell electron pair repulsion theory, right? Now, the few main points, the main points of this valence shell electron pair repulsion theory, let me talk about those main points, and at the end I'll show you the application of this valence shell electron pair repulsion theory, right? I'll show you how to apply it in the molecules, right? So that you can clearly say the shape of any molecule right here, yeah? Perfect guys. Now this is something which I've taught in the last session, okay? You can go to the hybridization session, right, which was 2 days back. Just check it out, you'll get to know, okay? Perfect guys, perfect. So the first point in case of your valence shell electron pair repulsion theory, what is it all about? Have a look guys. The shape or geometry of the molecule is determined by the repulsions between the valence electrons of the central atom, okay? What does that mean? Say, first of all, let's say I have got the molecule, let's take the molecule NH3, right? Let's take the molecule NH3, correct? Well people, if I ask you in this NH3, which one is the central atom? This nitrogen is the central atom, yes. And this nitrogen, it has got how many valence electrons? As you all must be knowing, it has got 5 valence electrons, right? These are the 5 valence electrons of this nitrogen, okay? Let me tell you, those electrons of nitrogen which participate in the bonding, I'll be calling those electrons of nitrogen as the bonding electrons, right? Those electrons of nitrogen which belong to the valence shell and participate in the bonding, those are what I call as the bonding electrons. And those electrons of nitrogen right here which belong to the valence shell but do not participate in the bonding, that's what we call as lone pair electron, right? I'm sure these two things are clear to you. Number 1, bonding electron. Number 2, non-bonding electron. Bonding electrons are the electrons which belong to the valence shell of the atom which participates in the bonding, whereas non-bonding electrons again belong to the valence shell. Non-bonding electrons, or we call them as lone pair electrons, right? Non-bonding electrons or lone pair electrons, these electrons again belong to the valence shell of the atom but do not participate in the bonding, right? Now we will see. If I talk about NH3, right, this nitrogen, it has formed 3 bonds with the hydrogen right here, okay? So if I ask you, is this nitrogen having any sort of non-bonding electron pair right here? Yes, it has got one non-bonding electron pair, one lone pair of electron you call it, yes? And people, as per your valence shell electron pair repulsion theory is concerned, whenever you want to know the shape of the molecule is entirely governed by the repulsions between these lone pairs, the repulsions between the lone pair, the repulsion between bond pair, and the repulsion between lone pair and bond pair. Whenever you need to predict the shape of the molecule, you need to keep one thing in mind. That's going to be the repulsions between the lone pairs, bond pairs, and bond pairs, right? So the shape of the molecule is entirely governed by the repulsions between these bonding and non-bonding electron pairs, right? Yes, I'm sure this point is clear to you. Okay. And remember guys, remember. Well, as per your valence shell electron pair repulsion theory is concerned, these electron pairs which consist of bonding as well as non-bonding, right? These electron pairs which consist of bonding as well as non-bonding, they arrange themselves in such a way that there should be minimum repulsions between them and eventually there will be maximum stability, right? This is point number 2, which I want you guys to take a note of, right? As per your valence shell electron pair repulsion theory is concerned, if you want to predict the shape of the molecule, you need to take into consideration the repulsions between the valence shell electron pairs, right? You need to take into consideration the repulsions between bonding pair of electrons and non-bonding pair of electrons. Yes, right? Now people, remember, every molecule wants to have that shape in which the repulsions between these bonding and non-bonding pair of electrons are minimum so that stability is maximum, right? This was the second point about the valence shell electron pair repulsion theory, right? Perfect guys, have a look. Now people, order of repulsion between these electron pairs. Remember, lone pair repulsion is maximum, followed by lone pair, followed by bond pair. This is the order of the repulsions which you need to remember from now onwards. Remember, the repulsions between two lone pairs is going to be maximum, followed by the repulsion between one lone pair and one bond pair, followed by the repulsion between bond pair and the bond pair, right? Yes, Anamika, you can still watch it, right? This is point number 2. Now talking about point number 3, repulsion increases with the increase in the number of bonds, okay? Whenever you'll be having two triple bonds adjacent to each other, right? Whenever you'll be having two triple bonds closer to each other, the repulsions are going to be maximum, followed by two double bonds, followed by two single bonds, right? The repulsions between two triple bonds are going to be maximum, followed by the repulsions between two double bonds, followed by the repulsions between two single bonds. This is one more point which I want you guys to take a note of, yeah? Right? Okay, one more thing guys, This is important. If a molecule contains bond pairs only, that means lone pairs are absent on the central atom of the molecule, right? That's what I'm talking about. See, if a molecule contains bond pairs only, that means lone pairs are absent on the central atom of the molecule. It is said to have regular geometry as predicted through hybridization. What does it actually mean? See, what does it mean? Remember, whenever I'll be talking about any molecule, right? If the molecule does not have any lone pair, it has only bond pairs, right? If the central atom of the molecule, it does not have any lone pairs, remember at that time, whatever is the expected geometry of the molecule, that is its actual shape. I'm sure this is clear to you, right? Once again, I'm repeating the same thing. Whenever I'll be having such kind of a molecule in which the central atom does not have any lone pair, at that time, whatever is the expected geometry of the molecule as given by hybridization, same is the shape at that time, right? I'm sure this is clear to everyone. For example, let me give the example as well. See, if I take the case of CH4, right? In case of CH4, people, your carbon is the central atom. Yes, your carbon is the central atom. So if I ask you, are there any lone pairs on this carbon? There are no lone pairs, 0 lone pair on this carbon, right? There are no lone pairs. Since in the outermost shell of carbon, there are 4 electrons and it has used all its 4 electrons for the formation of 4 different bonds, right? So this carbon, this central atom, it does not have any lone pair right now. Okay, and whenever the central atom of the molecule does not have any lone pair, at that time, whatever is the expected geometry of the molecule from the hybridization, same is going to be the shape. See guys, the carbon right here, it has got sp3 hybridization, so its expected geometry is what? Tetrahedral. Since the central atom does not have any lone pair right now, so tetrahedral geometry is going to be its shape as well, right? So its shape and geometry both are same right here and both are tetrahedral, right? Let me know in the chat box if this concept is clear. Exactly, your geometry is going to be same as that of your shape, right? Whenever the central atom does not have any lone pair, correct? Absolutely, absolutely. Moving on to one more point. I'll be explaining all these points again after some time when I'll be giving you the application part of this valence shell electron pair repulsion theory, right? Perfect. Moving on to one more point. If the molecule contains both lone pairs and bond pairs, then its geometry and shape will be different, okay? For example, let's say I've got the molecule as NH3. Let's say I've got the molecule as NH3, correct? As you must be knowing now, in case of NH3, nitrogen has got one lone pair. Since right here we have got 3 bond pairs and 1 lone pair right here, yeah? This is the lone pair which the nitrogen has, right? If I ask you what is the hybridization of this nitrogen right here, you'll simply say it has got 3 bond pairs, 1 lone pair, steric number 4, its hybridization is sp3, right? So, as per hybridization concept, what should be the geometry of the molecule? Geometry of the molecule is tetrahedral. This is the geometry which I'm talking about, right? As per hybridization, whenever there is sp3 hybridization, the geometry of the molecule is what? Tetrahedral. But its shape is not tetrahedral. As you all must be knowing, its shape is pyramidal, right? Its shape is pyramidal. I hope you know it, correct? Its actual shape is pyramidal, right? So why is it pyramidal? You'll get the idea in some time, yeah? The point is, which I want you guys to take a note of, the point is, whenever you'll be having a molecule in which there will be bond pairs, and apart from bond pairs, there will be lone pair on the central atom. At that time, the geometry and the actual shape of the molecule are going to be different, right? Yes, remember this. Now, next point. Talking about the next point. The molecule acquires a shape in which the repulsion between the electron pairs is minimum. This is something which I told you in the beginning itself, right? As per your valence shell electron pair repulsion theory, these electron pairs, these bonded pair of electrons and a lone pair of electrons, they arrange themselves around the central atom in such a way that there are minimum repulsions between them and the stability is maximum. So few minutes afterwards, you'll be seeing how I'll be arranging these electron pairs in such a way that there are minimum repulsions and maximum stability, right? These were some main points of the valence shell electron pair repulsion theory, which I'll be explaining one by one in some time. Before explaining them, let me talk about one more important thing. That's something which we call as bond angle. Yes? So people, this valence shell electron pair repulsion theory, it gives us the idea about the bond angles as well. As I told you in the beginning itself, the repulsions between lone pairs and lone pairs, the repulsion between lone pair is maximum, followed by lone pair, followed by bond pair, right? This is something which I told you in the beginning itself, right? Now guys, see, if I ask you what is the hybridization of this carbon, you'll simply say sp3, yeah, because it has got steric number 4 sigma bonds, 0 lone pair. What about the hybridization of this nitrogen? It's again sp3, right? And in case of sp3 hybridization, what is the expected bond angle? That is 109 degree 28 minutes. What is the expected bond angle right here? The expected bond angle again is 109 degree 28 minutes, right? But what happens when a molecule gets the lone pair? Right here, you have everywhere the bond pairs. You have everywhere the bond pairs, right? You have everywhere the bond pairs, correct? So people, in this case, you do not have everywhere the bond pairs. On this side, you have got the lone pair, right? So what happens basically, you can understand it like this, as if you have replaced this bond by a pair of electron. As if you have replaced this bond by a pair of electron in case of NH3. Yeah. Now people, can I say over here you will be having repulsions between lone pairs and bond pairs, right? And in this molecule, everywhere you will be having the repulsions between bond pairs, correct? Can I say repulsion right here is going to be maximum? right? If the repulsion between this lone pair and the bond pair is maximum, can I say these bond pairs will come closer like this? And if the bond pairs are coming closer like this, what is happening to the bond angle? What is happening to the angle between the bonds? Angle between the bonds will decrease. That is why in case of NH3, the expected bond angle is 109 degree 28 minutes, but it actually is 107 degrees. Yes, remember this as well. What is the reason? Due to the repulsion between lone pair and bond pair in case of NH3. Yeah, perfect. And remember, more the repulsion, more is going to be the, more the repulsion, less is going to be the bond angle. More the repulsion right here, more the repulsion between this lone pair and bond pair right here, less is going to be the bond angle. Less is going to be the bond angle, right? I'm sure this is clear to you again. Yeah. Moving on to one more thing. See, I've taken few molecules right here. See, you have got CH4, this is NH3, this is H2O, correct? CH4, NH3, H2O. Can you let me know the bond angle order right here? Can you let me know can you let me know in the chart box what is going to be the expected bond angle? I mean expected bond angle order, you can tell me that, right? Well people, right here, everywhere you have got repulsions between bond pairs, right? Everywhere you have got repulsions between bond pairs in case of CH4. Yeah. Over here you have got the repulsion between this lone pair and these bond pairs, correct? And over here we have got two lone pairs and two bond pairs, right? So first of all, there will be repulsions between these two lone pairs, and due to the repulsions between lone pairs, they'll come like this. And when the lone pairs come like this, the lone pairs come closer to these bond pairs, due to which these bond pairs come very closer. Yeah. So I'll say this H2O, it has got minimum bond angle followed by NH3 followed by CH4. Yeah. So remember, this has got the normal hybridization is Sp3, correct? Even this is Sp3, even this is Sp3. But what is happening right here? Bond angle in this case, in the first case is 109 degree 28 minutes. In the second case, it's 107 degrees. In the third case, it's going to be 104 degree 5 minutes. Remember this as well. So you can compare the bond angles like this, yeah? Can you let me know in the chart box if it is clear? Can you let me know in the chart box if it is clear so that I can move on to a few more interesting things? Right? Perfect, guys. Perfect. Let's get to know a few more important things. Effect of electronegativity on bond angle. Effect of electronegativity on bond angle. Just a second, guys. Just let me take this wire off from here. Okay. Effect of electronegativity on bond angle. Okay. The case number one, which I'll be talking about right here. When the central atom is different. See, I have taken three molecules right here, right? Over here, the central atom is nitrogen. Right here, central atom is phosphorus. Right here, central atom is arsenic, right? So I have got three molecules right here in which central atom is different. Whenever central atom is different, at that time, remember, bond angle is directly proportional to electronegativity of the central atom. That's what you need to remember, okay? When the central atom is going to be different, at that time, bond angle is directly proportional to electronegativity of the central atom. Very simple, yeah? Correct? So, see guys, right here I've got nitrogen, right here phosphorus as a central atom, right here arsenic. Can I say nitrogen has got the maximum electronegativity between phosphorus as well as arsenic, right? Nitrogen has got maximum electronegativity. So, more the electronegativity of the central atom, more is going to be the bond angle. So, you can let me know the order of the bond angles right here as well, yeah? So, order of bond angles is going to be, in case of NH3, it's going to be maximum, followed by PH3, followed by ASH3. So bond angle will be maximum in case of NH3, correct? Correct? Nafis, you need to talk to the operational team, bro. Right? But this is only valid, guys, if the central atom is different, okay? But the point is, if the central atom is same. When the central atom is same, for example, NF3, NCl3, NBr3. Right here the central atom is nitrogen, right here again central atom nitrogen, right here again central atom nitrogen. When the central atom will be same, at that time, remember, bond angle is inversely proportional to electronegativity of the central atom, okay? Exactly, Yasir, exactly. So in short, what you're going to remember, when the central atom is same, at that time bond angle is inversely proportional to electronegativity, okay? Not the electronegativity of the central atom, electronegativity of the terminal atoms, right? Yes? So people, have a look. Whenever, as I told you, whenever your central atom is same, at that time, the bond angle is directly proportional to electronegativity of these terminal atoms. Electronegativity of these surrounding atoms, I must say. Yeah? So over here, fluorine is the terminal atom. Fluorine has got the maximum electronegativity. If fluorine has the maximum electronegativity, so bond angle in case of first one is going to be minimum. Every single thing which I'll be writing over here on the screen. Yeah? Now we will see what I'll be doing. Understand properly what I'll be doing. First of all, few points which you need to take a note of. As I told you earlier, if I'll be having any sort of molecule in which there will be no lone pair on the central atom, remember, for that molecule, geometry is equal to shape. And how do we get to know the geometry? From the hybridization, yeah? From the hybridization, correct? Now understand. The first case which I have, I'm talking about the molecule in which the hybridization is, for example, sp2. Okay, I'm talking about those molecules in which the hybridization is sp2. This is my first case, right? Hybridization sp2 means steric number is equal to 3, right? Hybridization sp2 means steric number is equal to 3. 2 plus 1, 3, right? Steric number 3 means sigma bonds plus lone pairs is equal to 3, correct? Correct? So first of all, I'm talking about those molecules which have got hybridization of sp2. When is that possible? When the steric number is equal to 3, when sigma bonds plus lone pairs is equal to 3, correct? This is my case number 1. And in this case, my first sub case is I have got a molecule which contains 3 bond pairs or 3 sigma bonds, I'll say, or let me keep it as 3 bond pairs. I've got a molecule in which there are 3 bond pairs and 0 lone pairs, right? Okay, and I'm going to represent this molecule by A, B, sorry, just a second. I've got sp2, correct? Steric number is 3. Sigma plus lone pairs. Okay, 3 bond pairs and 0 lone pair, right? I'm talking about which molecule? I'm talking about AB3 molecule, right? AB3 molecule. I'm assuming this A right here is the central atom and these B's right here, these are the terminal atoms, right? So I've got the molecule which has got 3 bond pairs, 0 lone pairs. Or you can say 3 sigma bonds, 0 lone pairs, okay? So first of all, if you can see right here, this molecule on the central atom, you have got 0 lone pairs. So whatever is going to be the expected geometry, that is going to be its shape. So what is the expected geometry over here? What is the expected geometry over here? Since hybridization is sp2, it's trigonal planar. It's trigonal planar, right? It's trigonal planar. So expected geometry as per hybridization is trigonal planar. It's trigonal planar. And its shape also is going to be trigonal planar, right? So geometry is equal to shape. This is case number 1 in case of sp2, right? So I've got one more sub case in this one. I've got a molecule which contains 2 bond pairs and 1 lone pair, right? 2 bond pairs and 1 lone pair. How do I represent it? Or before representing it, let me show you exactly how this trigonal planar looks like. I've got A right here. For example, this is B. This is one more B, this is one more B, correct? They are going to make a triangle kind of a structure, yeah, like this. And all these 4 atoms, they are present in a single plane. Yeah? Now we will understand. I have got a molecule in which there are 2 bond pairs and 1 lone pair. 2 bond pairs and 1 lone pair, right? So how do I represent it? I'm representing this molecule as AB2L, right? It means A is the central atom, it has got 2 bond pairs and 1 lone pair, right? AB2L type, okay? So first of all, what is the hybridization right here? Since 2 bond pairs, 1 lone pair. So 2 plus 1, 3, that means steric number 3, sp2. In case of sp2, what is the expected geometry? This, over here I'm writing geometry, okay? Over here I'm writing geometry, correct? So what is the geometry right here? Geometry again is going to be trigonal planar, correct? But people, what is going to be the shape? Is the shape going to be again trigonal planar? No, I told you, simple guys. I told you simple. Whenever you'll be having a molecule in which the central atom has the lone pair, at that time shape is not going to be equal to the geometry, right? Yes, AB to L type. Can you let me know what is going to be its shape, actual shape? So what I'll be doing, understand how I'll be making its exact shape. See, I've got AB to L type, right? So people, I'm just going to keep A as at the center like this, okay? So among these three, I'm going to remove any of the bond pair, and instead of the bond pair, I'm going to keep what? I'm going to keep a lone pair. Let me keep this bond pair as such, this bond pair as such, and right here, let me keep a lone pair, right? So now you are going to see its actual shape, right? Leave this lone pair aside. Can I say it looks a bent molecule? Leave this lone pair aside. It actually looks like a bent molecule over here. So its actual shape is going to be bent over here. This is the actual shape. Its geometry is trigonal planar, but its actual shape is what? Its actual shape is bent. I'm sure this is clear? Yeah? Right? Perfect? Exactly. Now people, this was about sp2 hybridization, okay? Now let's talk about the second one. That is sp3 hybridization. The molecules in which hybridization is involved? In which sp3 hybridization is involved. If sp3 hybridization is involved, that means steric number is 3. Sorry, steric number is 4. Steric number means sigma bonds plus lone pairs, right? Or you can say bond pairs plus lone pairs is equal to what? Steric number is 4, correct? And if the steric number is 4, we know the expected geometry. Expected geometry is tetrahedral. I hope you know that, yeah? Correct? Now we will see. The first case which I'm taking right here, if I'll be having a molecule in which bond pairs will be exactly equal to 4 and lone pairs will be exactly equal to 0. Correct? 4 bond pair, 0 lone pair. That means steric number 4. Correct? What is the expected geometry as per hybridization? Since hybridization is sp3, so expected geometry is tetrahedral. Its geometry is tetrahedral. Its geometry is tetrahedral. What about its exact shape? So first of all, let me make its geometry. Its geometry is going to be like this. This is A, for example, this is B, and this is, for example, one more B, this is one more B, this is one more B, correct? AB4 type, right? It's AB4 type. Let me write it over here. Which one I'm talking about? I'm talking about the molecule which is of the type AB4. A is the central atom and it has got 4 bond pairs. There is no lone pair, right? So geometry is tetrahedral. This is the tetrahedral geometry over here. Okay, now people talking about the shape. Since lone pairs are 0, so whatever is going to be the geometry, same is going to be the shape. So right here in this case, shape is also tetrahedral, yeah? Correct? Similarly, in this sp3 hybridization only, there is one more case, right? In which there are 3 bond pairs and 1 lone pair. 3 bond pairs and 1 lone pair. Which type of molecule I'm talking about? I'm talking about the molecule AB3L type. AB3L type, right? A is the central atom, 3 bond pairs, 1 lone pair, correct? What is the hybridization right now? Since 3 plus 1 is 4, sp3. If hybridization is sp3, that means geometry is again tetrahedral, right? Geometry is tetrahedral. But is its shape going to be tetrahedral? No way. Why is that? Because the central atom has got the lone pair, right? So its shape is going to be different. And how can I guess its shape? See guys, how will I be guessing its shape? Understand. Since geometry is tetrahedral, now talking about its shape. Let me erase this part. See. The first I'm writing geometry, now I'm writing shape. See guys, its shape is going to be like this. See, this is A. Its geometry was like this. Tetrahedral, correct? Its geometry was tetrahedral. But is its shape going to be tetrahedral? No way. What I'll be doing, I'll be removing one of the bond pair right here, and instead of bond pair, I'm going to keep a lone pair right here. Yes, it's a lone pair right here. Now you need to check its exact structure without this lone pair. It looks like a pyramid, guys. If you join these two, if you join like this, it is going to be a pyramidal shape, right? So it is basically a pyramidal shape right here, as in case of your NH3, right? In case of NH3, you have got 3 bond pairs and 1 lone pair. I'm sure this is clear till here, yeah? Just Karthik, wait for it, yeah? Now people, talking about the third subcase of this one. What is the third subcase? Let's assume I've got the molecule in which there are 2 bond pairs and 2 lone pairs. 2 bond pairs, 2 lone pairs. Again, steric number 4, hybridization sp3. Which type of molecule is going to be? 2 bond pairs, 2 lone pairs. That means AB2L2 type. AB2L2 type, right? Yes. What is the geometry? Since the hybridization is steric number is 4, that means hybridization is sp3. Geometry is again tetrahedral. But what about its shape now? So from the tetrahedral geometry, I need to remove 2 bond pairs and place 2 lone pairs. Yes. See, if I make its tetrahedral geometry, it's going to be like this. This is A, B, this is one more B, this is one more B, this is one more B, right? This is the geometry of the molecule. So right here, what I'll be doing, I'll be just removing two bond pairs, and instead of the bond pairs, I'll be keeping what? I'll be keeping the lone pairs. That's it, right? So let me make it like this. Let me make its exact shape like this. Its shape is going to be like this. See guys, this is A, this is for example B, this for example B, there is one lone pair right here, there is one lone pair right here, as in case of H2O, right? As in case of H2O. So the shape is just leave these lone pairs. Now check its shape. It is going to be what? It's going to be a V shape or bent shape, right? Bent or V shape you call it, yes? Correct? I'm sure you're clear till here. I'm sure you're clear till here. Let me know in the chat box. Let me know in the chat box if everything is clear till here. Exactly, Gayatri, you're right. Let me know in the chat box with some thumbs ups so that I can move on, yeah? Okay? So this was about Sp3 hybridization, correct? Correct? Now, let's move on. Before moving on, just guys, let me turn the audio off. There is something wrong over here. People, you can let me know, am I audible and visible again? Am I audible and visible again? Like, am I audible? I'm so visible, I can see that from my phone itself. Am I audible? Yeah? All right, perfect. Now, let's talk about the next case. The next case which we are going to talk about the molecules in which hybridization is Sp3d, correct? We are going to talk about those molecules which have got Sp3d hybridization. That means steric number, which means basically sigma plus lone pairs is equal to 5. Yes. What is the expected geometry of these molecules? The geometry of these molecules, as you all must be knowing, it's trigonal pyramidal, right? It's trigonal bipyramidal, right? Trigonal bipyramidal geometry, right? Now, there are some cases in this which we need to take a note of. Correct? See guys, the first case, I have got a molecule in which there are 5 bond pairs. There are 5 bond pairs and 0 lone pairs. 5 bond pairs, 0 lone pairs means steric number is 5 plus 0 is 5. Steric number 5 means Sp3d. So what is the expected geometry? Geometry, you all know, wherever there is Sp3d, their geometry is going to be trigonal bipyramidal, right? So geometry is trigonal bipyramidal. How do I represent it first of all? If A is the central atom, how many bond pairs do I have? I've got 5 bond pairs. How many lone pairs right here? I've got 0 lone pair. You can write it as L0 as well, or you can simply keep it as AB5, yeah? Now people see, if I make the trigonal bipyramidal geometry, it's going to be like this. I'm sure you know it. This is A, this is for example B, this is for example B, this is for example B, yeah? All these 4 atoms, they are right now in one plane. They are in one plane. There is one B just above it, perpendicular to it, and one B perpendicular to it, but downwards, like this, yeah? This is AB5. This is what we call as trigonal bipyramidal geometry, right? Remember guys, these bonds which are present in the same plane, these bonds, this bond I mean, this bond I mean, and this bond I mean, these are present in the same plane. We call these bonds as equatorial bonds. We call these bonds as equatorial bonds, and these bonds which are perpendicular to them, these are what we call as axial bonds. These are what we call as axial bonds. And remember, axial bond length is always greater than equatorial bond length in case of what? In case of trigonal bipyramidal geometry, right? Remember this thing as well, yeah? Now people, let's try to understand few more things. I'm sure this part is clear. I was talking about, I have got the molecule in which bond pairs are 5, lone pairs are 0. That means the geometry is trigonal bipyramidal, right? If the lone pairs are 0, that means its shape will be also trigonal bipyramidal, right? So its shape as well as geometry right here are same, right? So let me erase this part. I'll simply say its shape and geometry is same, which is its shape and geometry is equal to same. I mean both are trigonal bipyramidal, correct? Now, one more case in this one. Let's say I've got the molecule in which bond pairs are 4, lone pair is 1. Bond pair 4, lone pair 1. Yes? So first thing, 4 plus 1, 5, steric number 5, that means Sp3d. correct? So how do I represent it? I'll be representing it like this, AB4L1, AB4L1. Yes, this is how I'll be representing it. Okay. Now people, understand. If the hybridization is Sp3d, its geometry is going to be trigonal bipyramidal. But what about its shape? What about its shape? Can you let me know what is its shape going to be? See guys, 4 bond pairs, 1 lone pair, AB4L type, where A is the central atom. These 4 are these 4 are the terminal atoms, and it has got central atom has got 1 lone pair as well. Exactly, Gayatri, it's a seesaw shape, yeah? For example, like this. Let me talk about its shape. See, this is the geometry. Now I'm talking about shape. This is, for example, A. Let me make its geometry first. This was B. This was one more B. This was one more B. And these 3 bonds were in a plane. There was 1 bond at the top. There was 1 bond over here downwards, right? Perpendicular to these equatorial positions, yeah? Now, people, this was the normal geometry of the molecule. Now, in this normal geometry, I'm going to remove this equatorial bond, and instead of it, I'm going to put a lone pair right here. Now, people, see, if I look at the molecule without this lone pair, can I say it looks like a seesaw shape? Absolutely, this is what we call as seesaw shape, right? This is what we call as seesaw shape. Example of it is SF4, yeah? So in case of AB4L type molecule, the geometry is trigonal bipyramidal. The actual shape is seesaw, correct? Right? Exactly, guys. Yeah? Now which case is left over here? I'll say the third case over here, that's going to be 3 bond pairs and 2 lone pairs, right? 3 bond pairs and 2 lone pairs. Can you let me know what is going to be the, first of all, let me know the type of the molecule. Can I say type of the molecule is going to be AB3L2? AB3L2, right? A is the central atom, 3 bond pairs, 2 lone pairs, AB3L2, correct? What is the geometry? Since hybridization is 3 plus 2, 5 steric number, that means Sp3d, so geometry is again trigonal bipyramidal. But what about its shape now? Can you let me know in the chat box? I just want to see if you can think about it or not. Exactly, AB3L2. See guys, how will I be making its shape? Understand properly what I am going to say. Okay, see first of all, in order to make the shape of this AB3L2 type molecule, I'm going to make its geometry, which is trigonal bipyramidal, which was supposed to be like this, for example. The geometry was supposed to be like this, yeah? Trigonal bipyramidal. But instead of two bond pairs, I'm going to remove these 2 bond pairs, and I'm going to place what? I'm going to place lone pairs over here. And how many lone pairs I need to place? I need to place 2 lone pairs, right? So instead of these 2 bond pairs, I'm going to place 2 lone pairs like this, yeah? Now just look at the molecule by just subtracting these lone pairs. So is it looking like a T shape? Just leave these lone pairs, right? It's looking like a T shape, so the shape of the molecule actually is T, right? It's a T-shaped molecule, correct? Yes? Correct. So the geometry is trigonal bipyramidal in this case, but the shape is what? Shape is T. Yeah? Right. Now, let's move on to one more case in this. I've got a molecule in which bond pairs are, for example, is there anything left? No, I don't think so, right? Is there anything left here? Okay, 2 bond pairs and 3 lone pairs, right? 2 bond pairs and 3 lone pairs. I've got a molecule in which there are 2 bond pairs and 3 lone pairs, correct? People, what is the steric number? 3 plus 2, 5. Hybridization, Sp3d. Which type of the molecule? It's going to be AB2L3. AB2L3 type, right? 2 bond pairs, 3 lone pairs, correct? Since steric number is 3 plus 2, 5, so hybridization is Sp3d. So again, the geometry is trigonal bipyramidal. But what about the shape? See guys, how the shape is going to be now. I'm sure this part is clear. What about its shape? Its shape is going to be linear. How come it's going to be linear? Understand. So in order to make the shape of the molecule right now, I'm going to make its geometry again. It's going to be AB5 geometry like this. This is B, this is B, this is B, for example, this is one more B, this is one more B. Now, this is the normal geometry of the molecule, correct? But what do I need to calculate? What do I need to see? I need to get the shape of it, right? So instead of, I have to adjust 3 lone pairs, and I have to adjust in this geometry, I have to adjust 3 lone pairs in such a way that there should be minimum repulsions between them. So let me remove these equatorial positions. Let me remove these equatorial positions. This is, for example, one lone pair. This is one more lone pair. And right here, you have got one more lone pair. So ignore these lone pairs. What is the shape? Shape is linear, right? As in the case of I3 negative, right? In case of I3 negative, hybridization is Sp3d. Hybridization is Sp3d. Okay. Geometry is trigonal bipyramidal. Shape is linear, right? Yes? Right. Okay. Now, this was Sp3d type. Now, which one is left? Sp3d2 type. Okay. Let's move on to Sp3d2 type. Just a second. Let's move on to Sp3d2 type. Yeah. Sp3d2 is possible only if the steric number is 6, right? Steric number, that means sigma plus lone pairs, right? And whenever there is Sp3d2 hybridization, what is the geometry of the molecule? That is octahedral. I hope you remember it. It is octahedral. Geometry is octahedral, I mean, yeah? Because from hybridization, you only get the idea of the geometry, not the shape, yeah? Now, people, the first case over here, I've got the molecule in which there are 6 bond pairs and 0 lone pairs. 6 bond pair, 0 lone pair. That means shape is equal to geometry. If the geometry is octahedral, shape is also going to be octahedral because it has got 0 lone pair over here. Correct? Exactly. See, guys, 6 bond pairs, 0 lone pairs. So first of all, what is the hybridization Sp3d2? What is the type of molecule? It's simply going to be AB6. A is the central atom and 6 bond pairs, right? AB6. Geometry and shape both are octahedral. Geometry and shape both are octahedral. And how do I represent it? Say, octahedral geometry, how do we represent it? This is, for example, A. This is, let's say, B. This is one more B. Okay. Let's keep it like this just a second. This is, for example, one more B. This is, for example, one more B. Yeah. These 1, 2, 3, 4. These 4 bonds are in one plane. There is a B just perpendicular to the plane like this, one more B perpendicular on this side, right? This kind of geometry is what we call as octahedral geometry over here. Yeah? Why do we call it as an octahedral geometry? Because if you join these things, if you join it like this, you get a perfect octahedron. You get a perfect octahedron, yeah? You get a perfect octahedron over here. Correct? Now guys see. Since there are 0 lone pairs, that means whatever is going to be the geometry, same is going to be the shape, correct? Shape as well as geometry in case of AB6 type is same, correct? And it's octahedral, yeah? Now we will see. The second case over here is if the bond pairs are 5, lone pair is 1. Bond pair 5, lone pair 1. What is going to be the type of the molecule? Is it going to be AB5L1? Yeah? AB5L1, this is the type. What is the hybridization? Since steric number again is 5 plus 1, 6, so hybridization is again Sp3d2, so geometry is again octahedral. Geometry is again octahedral. But is the shape going to be octahedral right now? No way, because it has got the lone pair. I mean, there is a lone pair on the central atom. The shape is not going to be octahedral. Now, from the geometry, I need to remove one bond pair, place a lone pair, right? Yes. Now, where do I place a lone pair? In this geometry, where do I place a lone pair? I need to place it in such a way that there should be minimum repulsions at the end and maximum stability, right? And that shape is what I call as square pyramidal shape, right? See, it's going to be like this. I'm talking about the shape of this AB5L1 type. Shape I'm talking about, right? This is A. This was your B, this was one more B, this was one more B, this was one more B, correct? Let's keep this B at the top, and instead of the B which was at the bottom, let's place a lone pair right here. So isn't it going to be a square pyramidal type? Isn't it going to be a square pyramidal type, right? We call this shape as the square pyramidal shape. We call this shape as the square pyramidal shape, right? Exactly, guys, exactly. So let's talk about the next one. Let's assume there are 4 bond pairs and 2 lone pairs. 4 bond pairs, 2 lone pairs means the type of the molecule is going to be AB4L2. Yes, AB4L2. So again, the steric number is 4 plus 2, 6. Hybridization Sp3d2. Geometry again is going to be what? Geometry again is going to be octahedral. But is the shape going to be octahedral? No way, because we have got a lone pair on the central atom, right? Now, people, from the octahedral geometry, I need to remove 2 bond pairs, and instead of those bond pairs, I need to place two lone pairs, right? And I have to place those lone pairs in such a way that there should be minimum repulsions, right? So let me arrange it like this. This is, for example, A, this was your B, this was your B, this was B, this was B over here, and these 5 atoms are present in one plane. There was a bond just perpendicular to it, right? So instead of that, I'm keeping a lone pair. Instead of the bond which was below it, I'm keeping a lone pair. So it is basically a square planar shape. Just ignore these two lone pairs. It's basically a planar shape now. And we call this shape as square planar shape. So remember, whenever we'll be having the molecule of the type AB4L2, its geometry is octahedral, but its shape is going to be square planar. Yeah? Right? Perfect, perfect, perfect. All right. Now the last case that is left over here is Sp3d3 type. Yeah? Sp3d3. Okay? Sp3d3 means steric number. Steric number, which is basically sigma plus lone pairs. Steric number is 7. Yes? Steric number is 7. And in case of Sp3d3, what is the geometry? Geometry is pentagonal bipyramidal. Pentagonal bipyramidal. And how do we represent this pentagonal bipyramidal geometry? See, let's say this is one atom at the center. Yeah, this one atom at the center. This is one more atom. 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 Right? Now the bonds between these atoms are, for example, like this. This is first bond, second one, third one, fourth one, fifth one, right? These green colored lines, these are not bonds, right? Okay, there is, for example, one more bond like this and one more bond like this. We call this geometry as pentagonal bipyramidal geometry. Okay, we call this geometry as pentagonal bipyramidal geometry, right? Now people, see what you are going to remember right here. Number one, the first case over here. The case is, if I'll be having, for example, I have got a molecule in which there are 7 bond pairs, 0 lone pairs. What is going to be the type of the molecule? Type of the molecule is simple, going to be AB7. If the type of the molecule is AB7, since there is 0 lone pair, so whatever is going to be the geometry, same is going to be the shape. Since geometry and shape right here both are going to be pentagonal bipyramidal. Yeah? Geometry and shape both are going to be pentagonal bipyramidal. Correct? Yes? Perfect, perfect, perfect. Exactly, Karthik. I have 7. I'll be giving you example in a while, guys. I'm going to give you examples in a while. Just I'm going to make you understand first these things. Yeah? Perfect. Similarly, if I'll be having a molecule in which bond pairs are 6, lone pair is 1. 6 bond pairs, 1 lone pair. What is the type of the molecule? The type of the molecule is going to be AB6L1. If the type of the molecule is AB6L1, its geometry again is going to be pentagonal bipyramidal. Yes, because hybridization is same Sp3d3. Yeah. What about its actual shape? Can you let me know? It's going to be distorted octahedron, right? It's going to be distorted octahedron. Just take one of the bond pair out. Just take one of the bond pair out and place a lone pair. You'll be getting it as the distorted octahedron shape. Okay. Now people, I'll be giving you few examples and you guys are going to let me know about their shapes and geometries. Okay. I'm sure yahan tak it's clear. I'm sure yahan tak it's clear, right? Now I'm going to give you few examples. And by giving the examples, you'll be letting me know the geometry, hybridization, shape, everything. Okay. See guys, the first molecule I'm giving you, BeCl2, a simplest molecule. Can you let me know what is the hybridization? What is the hybridization? Well guys, BeCl2, right? Yes, the hybridization is going to be what? Sp, I hope you remember that. Yes, hybridization is Sp. If hybridization is Sp, is there any sigma bond and lone pair? I mean, how many sigma bonds do we have right here? Just calculate the terminal atoms. So there are 2 sigma bonds and there is 0 lone pair. 0 lone pair on the central atom. Steric number value is sigma plus lone pair 2, right? Steric number is 2. Correct? Correct? What is the type of the molecule? Type of the molecule is AB2. Correct? Since there are 0 lone pairs, so whatever is going to be the geometry, that is going to be the shape, right? Whatever is the geometry, that is going to be the shape. What is the geometry? Geometry is equal to the shape and both are going to be linear, right? Both are going to be linear. I'm sure this is clear. Yeah. For example, I've got the molecule NH3. Correct? NH3. Yes, as you all must be knowing, nitrogen has got the one lone pair, right? Or let me erase this one. I've shown you in the last session how do we calculate bond pairs and lone pairs, right? I hope you remember that. I hope you remember that. Let's say I've got NH3. First of all, how many sigma bonds do we have here? 3. How many lone pairs do we have? We have got one lone pair right here on nitrogen. If I ask you about the steric number, what is the value of steric number? Sigma plus lone pair, 3 plus 1, 4. 3 plus 1, 4. That means geometry is what? Geometry, if I talk about the geometry is 3 plus 1, 4, tetrahedral. Geometry is tetrahedral. Okay, what about the shape? What about the shape? For the shape, I need to understand the type of the molecule. It is AB3L1, right? AB3L1. AB3L1. What about the shape? Now you can tell me the shape. AB3L1 is what? It is pyramidal, correct? It is pyramidal, correct? Yes? I'm sure this is clear. Okay. Now people, if I ask you about something as PCl3. PCl3. First of all, phosphorus again has got one lone pair. Yes. I think everything is same as that of your NH3. Everything is same. One lone pair, 3 bond pairs. That means one lone pair, 3 sigma bonds. Steric number again 4. Geometry again tetrahedral. Type is going to be AB3L1. The shape is going to be pyramidal, right? Same. All right. Let me give you a few more. Let's say I've got something as CH4 positive. Or let's keep it as NH4 positive. NH4 positive. I'm giving you simple molecules. NH4 positive. Give me everything about this molecule. You can do that. You can do that, right? So first of all, is there any lone pair on nitrogen? In the last session, I've told you how to calculate the lone pairs and bond pairs, right? So directly I'm saying you have got 4 sigma bonds. You have got 0 lone pair. 4 sigma bonds, 0 lone pair. That means steric number is 4 plus 0, 4. Hybridization is Sp3. If hybridization is Sp3, the geometry is tetrahedral, right? And what about the shape? What about the shape? Since 0 lone pair, whatever is the geometry, same is the shape, correct? And if I ask you what will be the bond angle, you will simply say 109 degree 28 minutes, yeah? Correct? Correct. Let me give you a few more examples. Let's say I've got something as SF4. SF4, correct? In case of SF4, if I ask you about like whatever information you want to give about SF4, you can do that. See, first thing, how many sigma bonds? 4 sigma bonds, yes. 4 sigma bonds. How many lone pairs? 1 lone pair on sulfur, right? If I ask you about the steric number is 4 plus 1, 5. If the steric number is 5, what is the hybridization? Hybridization is Sp3d. Okay. If hybridization is Sp3d, what is the geometry? Geometry is trigonal bipyramidal. Yes. What is the type of the molecule? It's going to be AB4L1. It's going to be AB4L1. Okay. If it is AB4L1, what is the shape? What is the shape? What is the shape? What is the shape? Shape is seesaw. Correct? Seesaw shape. I'm sure this is clear. Yeah? Right? Exactly. Let me give you a few more examples so that everything gets clear to you. Okay, one simplest example I'm giving you. Tell me about carbon dioxide. Tell me about carbon dioxide, CO2. Okay, first of all, how many sigma bonds here? 2 sigma bonds. How many lone pairs on carbon? 0. Okay, 2 plus 0 is 2. Hybridization Sp. Right? If hybridization is Sp, what is the geometry? Geometry is linear. Right? Since 0 lone pairs, that means whatever is the geometry, same is the shape. Yeah? Let me take few more examples. Let's say we have got something as XCF4. XCF4, tell me everything about this XCF4. First of all, how many sigma bonds? 4 sigma bonds. How many lone pairs? There are 2 lone pairs on xenon, right? 2 lone pairs on xenon. So 4 plus 2, it comes out to be 6. Steric number is equal to 6. If steric number is 6, that means hybridization is going to be Sp3d2. If I ask you which d orbitals are involved right here for hybridization, you can simply tell me dx square minus y square and dz square, right? And apart from that, Sp3d2, what is the geometry? Geometry in case of Sp3d2, geometry is going to be simply octahedral, right? If geometry is octahedral, what is the type of the molecule? It's going to be AB4L2. AB4L2, and in case of AB4L2, what is the shape? Shape is going to be what? Square planar, right? All this data you can conclude, yeah? Correct? Exactly. Let me give you a few more examples. Let's see. Let's see if you can solve it. Let's say I've got the molecule as XeOF4. Sorry, let's keep it as, yeah, XeOF4. 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 Let me know fast. Let me know fast. Let me know fast everything about this XeOF4. Yes, Rohit, you can do that. Yes, you can watch these. No issues. People, let me know fast. Let me know fast. I'm looking at your chat box only. Why is my YouTube hanged from my phone? Okay, perfect. Exactly, guys. All of you are right. All of you are right. Correct? 5 bond pairs, 1 lone pair. Yes? Sp3d2. Geometry octahedral. Shape square pyramidal. Yeah? Correct, guys. Let me write it over here. So first of all, what do I need to check? I need to check the sigma bonds, right? So how many sigma bonds? 5? Yeah. How many lone pairs? 1. Steric number 5 plus 1, 6. That means Sp3. Sp3d2. Geometry. Sp3d2 means geometry is octahedral, right? What is the shape? Shape is going to be square pyramidal, yeah? Square pyramidal. I'm sure this is clear now, yeah? Let me give you a few more examples so that everything gets clear to you. For example, I have got the molecule as I3 negative. Give me everything about I3 negative. Then I have got ICl4 negative. Okay. Then I have got, for example, BRF3. Yes, BRF3. Then I have got, for example, something as something as PCl5 in gaseous state. Okay, PCl5 in gaseous state. Okay, you can easily let me know about these. First of all, in case of I3 negative, how many sigma bonds do we have? We have got 2 sigma bonds. How many lone pairs do we have? 3 lone pairs. If I ask you about the steric number, 3 plus 2, 5. If steric number is 5, hybridization is going to be Sp3d. dz square is involved in hybridization. Its geometry is going to be simple trigonal bipyramidal. And what about its shape? What about its shape? Its shape is going to be of the type of AB to L3. If it is of the type AB to L3, shape is going to be linear. Right? Yes? Perfecto. Right. Yeah? Okay? Perfect, guys. So, this one, and one more, that is PCl5 solid. This is PCl5 gas, this is PCl5 solid. Do let me know their hybridizations, their geometry, their shapes in the comment box. Right after this session, okay? This is your homework and I'm damn sure you can do it, right? Right? Yes, so let me tell you about this PCl5 and PCl this 5. See, remember, whenever PCl5 is in gaseous state, it is considered to be covalent. And PCl5, you can say in gaseous state or in vapor phase, okay? Covalent. PCl5 in solid state, it is considered to be ionic. It is considered to be ionic compound. And PCl5 in solid state, how does it exist? It exists in the form of PCl4 positive, PCl6 negative, okay? PCl5 in solid state exists in this form, whereas PCl5 in gaseous or vapor state, it is covalent, it exists in the normal form, yeah? Okay, you can let me know about everything over here. Yes? Perfect. All right, guys. So this was all about the valence shell electron pair repulsion theory. I'm sure you would have enjoyed the session. Yeah, same. I did the same. Well, tomorrow it's going to be the session for organic chemistry, and tomorrow we are doing hydrocarbons, I guess. Yeah, are we doing hydrocarbons? Yeah, in the last session of hydrocarbons, what did we talk about? We talked about Oakwood process. Okay. Yeah, Cole's electrolysis and Oakwood process we did in the last session, and in the tomorrow session it's going to be again your hydrocarbons, right? Right? Perfect, guys. So for the ones who are new to the channel, well, this is the last option and the best option to shoot up your rank, to shoot up your performance for the NEET 2021. Trust me on that, okay? And people, the ones who are going to write the NEET in 2021, this is just for you guys. This is just for you guys. The first benefit, you're going to get trained by the teachers of your choice in your physics, chemistry, as well as your biology, right? No need to worry about the test series. No need to worry about the mock tests. Everything is included right here, okay? It's going to be a two-way learning interactive platform wherein you can ask your doubts anytime to your master teachers, right? And at the same time, guys, we are going to cover your whole syllabus before the NEET 2020 examination through the actual Vedantu platform. Apart from these YouTube sessions, right? You'll be having the personalized mentors in all the three subjects, okay? So this is the best thing and the last option which you can have right here. Okay, so do get enrolled in this. It's my personal suggestion for this, guys. Okay, do get enrolled in this. It's definitely going to be beneficial for you. Okay, right? Perfect. So how to get enrolled in this one? You just need to click on the Vedantu app. After clicking on the Vedantu app, just click on the NEET crash course. And after clicking on the NEET crash course, if you want me to train you, do not forget to use this coupon code WSNEET. After using this coupon code of WS, Wassim Sir NEET, right? Okay, after using this coupon code, you'll be getting 30% off. And after the 30% off, you are just getting this crash course for 7K. That's it. Okay. So people, my personal suggestion for you guys is to get enrolled in this one because then only, I mean, you can shoot up your performance by 30 to 40, I'm telling you, for sure, okay, in your NEET 2021 examination, right? At the same time, the next batch for the NEET 2021 crash, it's starting on 3rd of May. Link is there in the description box of the video. You can click on the link as well, get enrolled, okay? And there is a Telegram link in the description box as well. You can click on that link, get added to the Telegram group and stay updated about the classes. And for the ones who have not liked the video yet, please do like the video, share and subscribe the channel at the same time so that everyone gets benefited out of these sessions, which I always say in every session. Yeah, people, do not forget to subscribe this channel. Okay, do not forget to do that. Just subscribe the channel so that you get the notification of every single session which will be taking right here on this channel. Okay, it was nice meeting you. I'll see you guys tomorrow at the same time, 7:30, and tomorrow it's going to be hydrocarbon lecture number 3. Okay, till then you guys can take care. Bye bye. God bless you all and love you all. Take care. Bye.